Welcome to the Human Ideasphere series, Chapter 5, Energy, Part 2. In our last session, we left our baby universe as a swirling mass of energy and the idea that energy can do only one thing. It can move. That's it. Everything that formed after the Big Bang resulted from energy's ability to move. Everything. All energy particles can do is run into each other and let things happen. As energy particles moved outward after the Big Bang, they created space. That is, the particles from the Big Bang dissipated, leaving relatively empty areas in between. At first, energy particles were so close together and moved so fast, the particles just bounced off each other. But in a very short time, as the particles spread out, the hot, fast-moving energy that smacked together could not come apart in a cooler environment. This is a very rudimentary explanation of how simple energy particles grew more complex with time. When the universe was around 380,000 years old, this is what it looked like. It was a hazy, opaque, flattened oval filled with dark energy, dark matter, forces, and subatomic particles, including proton-neutron groups. Around this time, a very interesting thing happened. The universe cooled so much that the electrons, which had been flying solo in this grand mix of particles, became attracted to the proton-neutron groups and formed hydrogen, what we know as the first and smallest element. Hydrogen is an extremely stable unit of matter in the visible universe. Its charges are balanced, its nucleus is bonded tightly by the strong force. In a universe that was steadily cooling, hydrogen was an element not likely to come apart. This is still true today. In our universe today, hydrogen still makes up 92% of all visible matter in the universe. Here's another super interesting thing about this moment in time. All the light you see in this picture was created by those loose electrons running around. They scattered the light so it couldn't move in a straight line. But once electrons bonded to protons to make hydrogen, they could no longer scatter the light, and the light was free to move. And move it did. It shot out in every direction. It is still going today, though it has weakened and cooled with time. We know it today as cosmic background radiation. It can be detected as microwaves coming from the farthest distances of our universe. Once the light left, the universe became transparent and very dark. This time period is called the Dark Ages, as noted in this picture. Space wasn't empty, it was just dark. It was loaded with stuff we can't see and can barely detect. Dark energy, dark matter, vacuum energy, the Higgs field, which gives matter its mass, and space curvature, which is how gravity exerts itself on matter. And there was hydrogen. To give you some perspective on where we fit into the universe, our solar system and Earth were formed at about 9.3 billion years old. As we know, energy always moves, so change kept happening. Hydrogen atoms floated around, and gravity pulled them together. When this happened, two of our forces squared off. Gravity attracted hydrogen atoms together, but when the hydrogen atoms got too close to each other, the strong nuclear force within the nucleus of each atom pushed back on gravity. A standoff occurred. If enough hydrogen atoms were attracted to each other, the force of gravity would exceed that of the nuclear force. When that happened, the hydrogen atoms would collapse inward, pressing their nuclei together and sending the electrons and light flying outward. We know this as a star. Hydrogen fuses to make helium, and the electrons emit light as they flee. That is, the star shines. Stars have their own life cycle. Gravity continues pressing on the hydrogen atoms and fusing them into helium, which is an atom with 2 protons and 2 neutrons. When all the hydrogen is used up in the immediate area, gravity gets to work on helium, fusing it into carbon or oxygen. This is how the universe creates the middle range elements. When a star gets to the point where the element iron is formed, an interesting thing happens. Iron absorbs energy during fusion, which means an iron atom cannot offset gravity by pressing energy outward. The result is a double dose of energy pushing inward on the atom. One of two very large changes will occur. If the star is small, it will collapse into a dwarf star and slowly stop shining as it uses up all its fuel. But if the star is really big, it explodes into what scientists call a supernova. In a supernova, the elements are smashed together in the explosion. This is how elements heavier than iron are created. These heavy elements form, and when the energy from the explosion ends abruptly, they are stuck in their larger configuration. If they get caught up in another star and blow up again, even heavier elements and even some simple molecules will form. Interestingly, our sun is at least a third-generation star. That means the material that makes up the sun has joined and exploded at least 2 times before it has settled into its current configuration. With all those nice heavy elements hanging around, it's not a surprise that some collected and fell into gravitational rotations around the sun. These are planets. Solar systems like this exist all over the universe. The Earth in our solar system is just one of billions and billions of planets that exist across the universe. Okay, this is a very general story of the beginning of the universe. I spent a little bit of time here because it's really important. The energy that created dark energy and dark matter and visible matter is the very same energy that created Earth and life and humans. Next time, we're going to look at the attributes of energy. And you're going to find that humans are connected not only to all life forms, but we are connected to all energy in the universe. Until then, bye. Thanks for joining me.